It's Todd Harrison from ToddFun.com. I'm going to try something new. I'm going to try and do a little bit of a what am I doing video blog, as opposed to writing up and posting everything with just photos and short videos. This is going to be a little bit about this power supply control module repair. Now, if you've been following the blog and the write-ups and some of the photos, you'll know that I've been kind of, well, when I had free time, I've been trying to work on this little control module, which is also a little power supply for this motor, which you should be able to see off camera here. This is a motor and a power supply control module from a treadmill, but it was modified by a hackerspace called Heatsink Labs to actually be used for a tabletop lathe. During one of their cutting jobs, they got a little bit of metal inside this power supply and poof. So they asked me if I could look at it. Well, sure, why not? It's a simple power supply. It's a very simple power supply. But I figured a fuse. Well, no, they checked that. And then I'm like, well, yeah, sure. I'll bring it by the lab here. I'll poke at it a little bit. You'll find a bad transistor, maybe a bad cap, maybe a blown trace. Easy fix, done deal. Well, no. It's anytime I've had a little bit of free time, I end up working on this little control module power supply, and I run into headache after headache. My first whack at this was, well, I'm going to check all the passive components. I'll check all the capacitors, I'll check the transistors in circuit. I know that's not the best way to do that, but it's fairly reliable. You find them once in a while that way without tearing them out. I'll check the power transistors, give you a close-up of the board. Some of the things you check right away, of course, is you check the fuse. That's good. You check some resistors. You check some capacitors like this large cap. You make sure that these caps look bad, like they're not leaking. Make sure that they test out the right capacitance, which they did. Now, there's a few straightforward resistors that you want to make sure at least in spec. There's these power transistors. They were okay. This is actually a diode. It's okay. I checked, of course, the motor. It was fine for the lathe. Of course, all the traces were good on the back, and all this ink marking, if you've seen the blog earlier, all this inking is me basically tracing this all out one little line at a time and putting it on paper to find out exactly what is the logic going on this control board. Because this is actually a control board that controls the speed of the motor, like it was originally on a treadmill. As well, it provides the power. It's a really dumb power supply. It has a bridge rectifier right here, which actually was testing out originally good, but it was getting hot when I was doing some testing, and as you noticed in the previous blog, this actual bridge rectifier, which converts the AC signal into a DC source, actually blew up on me. And it actually blew some traces on the bottom, and as you'll see, I have a little patch right there where I had to clean it up and patch the trace. I pulled a bridge rectifier out of an old power supply. I have them laying around all over the place. So then I figured, well, heck, this thing it's pretty dangerous working with a 120 volt power supply. You don't want to poke the wrong spot. You don't want to get your finger on the wrong spot. It's dangerous. So I thought, well, okay, enough of that. I know the passive components are pretty decent. I don't see anything really wrong with it. Traces are pretty good. Caps are good. Transistors seem all good. So I figured, well, I'll just drop by Circuit Specialist, grab a few of these chips that are on this board, some of the control chips, which is like a pulse generator and an op amp and stuff. You look on the other posts of my previous posts, and you'll see where I go over exactly what those chips are. And I just unsoldered them and soldered in the new ones. And figured, well, it's enough piddling around to get the new chips in there. They're probably bad. One of them's just bad. And well, I turned it on, nothing. Still nothing. And the motor's not turning. Well, I knew from originally that the problem was that the pulse generator that actually pulses these power transistors on the side, well, it wasn't coming out. I wasn't getting the pulse signal that actually turns these power transistors on and off. And that pulse generation comes from that chip. So I know there's a problem in there somewhere, so I was for sure that replacing the chips would just, poof, you figured it out, it's done. But it didn't. So now I'm even more perplexed. It gets hard at this point. It gets hard because you really do have to now start probing around again, which I'm fine with, but being this I already blew it up on me once, I wasn't so keen on, you know, standing beside it and probing it again, knowing that it does get hot. You know, while it's in some state of non-functionality, this thing's getting hot. And, well, you don't want to be standing beside a power supply that's getting hot, you know. Okay, I got my first test going here. This, by the way, is the motor for the treadmill that's been converted into the lathe motor. This is a circuit under test. What I got right now is got my cooling fan running, trying to keep it a little bit cold, while I'm actually measuring the current flow into this thing in this sort of non-functioning mode. And you see it's about 0.039 or 39 milliamps is what it's running at, and that's basically just no load. It's not doing anything. The circuit can't do anything, and we know that's good, so we'll move on to the next part. Okay, now we're going to check our bridge rectifier. We basically hooked across the what should be the rectified part of the bridge rectifier, which means we should be getting only positive pulses at the circuit from this bridge rectifier. This large cap will smooth that out along with the smaller cap. We'll make it nice and smooth, and we should be seeing somewhere around about 160 volts DC. We'll start with AC to show that we no longer have an AC signal. Let me turn it on. Okay, so we're on. We have the fluke set to an AC signal, and as you see, we see pretty much no AC signal because it's being rectified. We'll switch that to DC, and there we got 160. We get 175 volts DC. So there's plenty of voltage coming through this device. We'll check the next point. Okay, now we're hooked across one of these power transistors. There's two of them. They actually basically work essentially in parallel, so that when the pulse width modulator chip, which is this guy back here, that chip right there, when he pulses, the control gate on these power MOSFETs here, we're looking at the back side, this heat sink side, these basically get turned on and provide essentially a dual path to the motor lines here, this red and black motor line which come up to the motor. So what we're doing now is we're basically going to see, well, do we have that DC voltage sitting at this power MOSFET on the, essentially in this case it's going to be the middle leg and the bottom leg, which is how the data sheet says is going to be essentially the source and the drain are essentially, and then the gate is going to be the top. Is going to be the top pin right here is the gate control. And that's going to basically turn on when that small pulse width modulation comes on. Now I'm pretty sure that these only get turned on 50% of the time. They don't get turned on hard. The reason I think that is because there's nothing in this circuit here that's going to basically knock that 170 voltage down DC to what this motor is rated at. As you see, I don't know if I can see it on here, but this motor is rated at 90 volts DC. Well, that's not no good if you're going to be sticking 170, 160 plus DC into it by this type of power conditioning. So what they're going to basically do is they're going to turn these on 50% of the time minimum, thus providing at least half the power and not overdriving that DC motor. And then if you want to go slower, you'll basically be able to control that pulse width modulation chip through some resistor controls that plug in back here to essentially a pot that you essentially just turn the pot and you turn that pulse width modulation timing down to these power transistors. So what we're going to do now is we're going to turn the power on, and we're going to make sure that we are getting that voltage here. It was 170 something. And okay, I turned it on, and we are getting, well, pretty close to 170 volts DC. It's a pretty bad glare there. Is what's actually coming to that power transistor. So if the circuit was working, if that pulse modulation generator was actually working, it would be turning these on right now and this motor would be driving. So that's good. Okay, we're a new day and we're back in the lab. I'm ready for a few more tests. Today I'm going to try and make sure the motor's actually working, see exactly what voltage I'm getting at the motor, and then I'm going to do some tracing of other voltages. Essentially the law of working with electronics is thou shalt always check your voltages. I've heard that from a few people in my time. So we'll do that. Okay, we got a bit of a test set up here. This is the motor, the 90 volt DC motor. This is a part of the actual original control with the pot. This is the pot that you turn the speed up and down with. It's hooked into the circuit now. I also have a cooling fan, I think I showed you earlier. It's just blowing air over top of this board just to keep it a little extra cooler. I do not have the motor connected right now because what I have is I have a black and a red hooked into my Fluke. I'm going to then show that even when the circuit's turned on, we do not get a DC voltage at the motor, meaning that the motor is not getting that signal to have the voltage. So we'll do that now. Turn the powers on, we'll turn the Fluke. First of all, of course, there should be no AC at all. Looks like there's about 2 volts of AC riding on that line. And we have like 1 volt of DC, so that essentially is proof positive that it is definitely off. Okay, as we've said earlier, these are the transistors, the power transistors, that actually supply voltage to the motor connects, which are right in here. So you got a motor connect right there and a motor connect right there. And if these 2 power transistors, this one and this one, were actually getting power from this pulse width modulation chip right here, it would be coming down and it would be turning the gates on these 2. Well, I'm not getting a signal at this pulse width modulation, so I know there's problems back here in the control, in this control area back here. But I just want to test my motor real quick. Now, I've already tested across the bridge rectifier, which changes our AC into a DC source, changes it to about 170 volts DC, and confirmed that that's a pretty good signal, about 4 volt ripple across them. And I also confirmed that that is getting to these power transistors, but they're not turning on. So what I really want to do is test my motor. Now, I do have a DC power supply that would be more than enough to test the motor, but I'm going to show a little trick. I'm going to actually essentially just bypass these transistors by simply doing what their job is. Their job is to be turned on by the gate, by a small gate voltage. They get turned on and they pass all that current through this to the motor. So I'm going to do I'm basically going to just say, hey, I'm going to bypass these and do the job for them by just shorting across the source and the drain, essentially completing the circuit. It's like taking this out of the circuit altogether. Now, that's not exactly an advisable thing to do because this DC motor is not rated for 170 volts. But the way this works is it actually pulses at 170 volts on and off at least a maximum of a 50% duty cycle. So this thing is getting that 170 volts anyway under normal operating mode. But because it's only getting half of the time, the motor basically just sees it or runs as if it's getting a nice DC 90 volt signal. So if I turn it on quickly, if I actually jumper across the transistor to essentially supply the power, this motor should kick in and should run, and that shows me that the motor does work. But I could also use my power supply, but some people don't have a high enough power supply to do that test. Okay, I have the AC power hooked up again, and you probably can see here I have a jumper going from the source to the drain, to the source, and I'm not doing anything with the signal line, of course. And when we turn this on, this should, at least for a brief moment, it should engage our motor. And the circuit for that is this. Essentially, you have upside down. You have the source and the drain. This is the control gate here, where it actually should be getting the pulse width signal to turn on and off, to turn this power transistor on and off. What I've done is I've shorted across these 2 legs with a jumper, essentially bypassing the transistor. And if everything else about the power conditioning is correct, the motor will get a brief pulse of power when I flip the switch, and everything should be working fine for the motor. But you don't want to hold it at that for more than just a brief second, because that is way too much voltage for this motor. Okay, and we're ready to run this quick little fast test of the motor. There, you could probably see it turning on. Okay, I pretty much know that I'm good to go with the power conditioning for the motor. The power transistors aren't turning on, so that leaves the control part of the circuit. You know, why is the control part of the circuit not working? So first, once again, check your voltages. So what I got right now is I got a red and a black hooked up to what's basically the ground plane of this circuit after the rectification, and the red one is hooked up to basically a point-for-point spot that hooks up to the power VCC end of the chips. So for the pulse width modulation chip, this is the pulse width modulation chip that's supposed to be pulsing those power transistors. I have essentially pin 5 is ground per the data sheet, and pin 6 is the pulse width output, and pin 7 is the VCC that should be giving the power to this chip. So my next thing is I'm testing the voltage, the DC voltage between 7 and 5 to see what type of voltage I get between VCC and ground. And that'll be my next voltage test. And I'll turn on, should be in the AC, of course, very little. And I am getting voltage. I'm getting, if you can see, getting right at about 17.6 volts DC. So that chip is getting power. Okay, we have the same exact test point here, but we've got two oscilloscope probes hooked up. Rather than testing straight with this, which did show we had about, I think it was like 17 volts DC. I want to see that with the scope now. Rather than hooking up a single probe with a ground clip, there's possibilities that there's lots of floating voltages on this board, especially if there's something wrong with it. So to be safe and to avoid any floating voltages issues, I'll use two probes. I'll use the yellow probe and the blue probe, and I will use the oscilloscope to do the difference between them. And essentially the difference between these two test points is the same voltage as if you had used a single probe with a ground clip, but it avoids the problem of having your ground clip hit a floating voltage that would, of course, short out through the chassis of your oscilloscope and cause quite a disaster. So these two probes are hooked up to that same test point, which is actually the voltage test point for the VCC on the pulse width modulation chip. And then over here we have the scope. I'm hoping the glare isn't too bad. And what we're seeing in the scope here, it looks a little complicated, but we have the yellow and the blue. Yellow is channel 1, blue is channel 2. I have the waveform for the yellow and the blue, and you can see they look like they're very close, but over here this is the point where it says that this is the ground point. This is what would be considered the ground point between that test point and the chassis of the oscilloscope. But I put both of them there, and that slight difference is what the probe is calculating up here. Now these two waveforms, the blue and the yellow, are both at 50 volts per division, which you might be able to see here and here. And so that you can get this whole 170 volt swing in between those 2 points. But they're testing between the chassis of the oscilloscope, so that doesn't really make any difference. What's truly there is this signal. Now this is the difference. The red bar is the difference between those two. If you look real closely, if each one of these segments is 50 volts, you can easily see that's right around 20 volts. The scale on the difference, though, is set at 5 volts down here, and the actual ground for this signal is over here, right there. So at 5 volts per division from this point, it's 5, 10, 15, not quite all the way up to 20. It's kind of jostling. It's got kind of a real crazy, what's called a ripple on top of that at that point. Right at where it would be essentially, if it was nice, smooth, perfect DC, it would say like 15 volts DC. But because this is rectified and cleaned up with some capacitors, you have this ripple, this really bad ripple. Now, went ahead and set the math up for the oscilloscope, and it shows that the actual average value at this point right here, the average, if you take out the ripple, is about 17.8 volts. The minimum that it's getting down to as it's pulsing is 14 volts. The maximum it's pulsing up to is about 20 volts. The peak to peak, this is the ripple, is 6 volts. So you think this would be about 6 volts. And if this is 5 volts per division, you can see that that is definitely peaking between those two parts, and that's 5 volts peak to peak. So the oscilloscope shows what we've already really knew already with our voltmeter, and that is that we do have a fairly nice, but very noisy 4 volt to 8, well, it's like 4 to 6 volt peak to peak ripple on about a 17.7 volt DC rectified signal going into those chips. Can the chips handle that? Well, that's pretty noisy, but I don't think that's our problem. Okay, I'll do some more voltage tests, specifically on that pulse width modulation. That's the chip that has to be sending that pulsed signal to the power MOSFETs, or the motor's just not going to turn. Until I can figure out why that pulse width modulation output pin is not actually producing that signal, I'm not going to get this figured out. So I went right to that chip, and that chip has there's other control circuits. There's other bits of control on this control board that actually control that tell that pulse width modulation chip what duty cycle to use. And it's not that complicated really, but it comes down to this pot right here on the side of this box. There's a knob, and you stick that knob in there and you turn it, and it's just a pot, and and the rest of the control circuit is measuring that pot and sending that signal to that pulse width modulation, and the pulse width modulation chip is comparing a couple voltages to decide what its duty cycle should be. So I went right to that chip and I measured the pins. So here's what I got for the voltages. Let's see if this focus is decent. I have the pulse width modulation chip. It has 8 pins. On this side, pins 8 through 5. It's VREF, which is 5 volts. It's always 5 volts. VCC, which is our 17.8 volts DC. It's dirty. It's got some ripple in it really bad, but it's there. This is the output that should be pulsing, but it's 0. This is our ground, and that checks out fine. On this side, pins 1 through 4, we have comp, VFB, current sense, and RT over CT. Now, the two that are varying, or pin 1 and pin 2, those two are varying, essentially comparing the two as that pot is turned. iSense is always basically pretty near 0 volts as far as that's concerned, and RT over RC is always at 2 volts. So I took measurements of the pot at 100% one way, 50% turned, and basically 0% all the way to the other side. So the only pins that actually changed are, the only pin that actually changed is pin 2, the VFB. It started at 100% pot turned one way was 2.5 volts, 50% it was 2.36 volts, sometimes 2.3 volts, and all the way to the other way, all the way basically down to about 0% on the pot, 1.78, or essentially it almost matched the compare chip on compare pin 1. So Now it's off to the data sheet. Look at this pulse width modulation chip. See, based on these inputs and this voltage reference variance, should it be outputting, and of course that voltage in, should it be producing a pulse? If the data sheet says yes, then my new pulse width chip is no good. If this says that there's supposed to be a larger voltage here or some other mechanism going on to make that fire, then I'll have to figure that out. I'm not real familiar with this particular pulse width modulation chip functionality at all. Well, I guess that's it for the evening. I've done due diligence on testing the voltages. The voltages for all of these ICs are right at about 17.7 volts. The ripple's really bad, but it should be plenty good to power these chips. So not a problem there. We definitely have the 170 volts DC for the motor. That's there. We tested the motor. It runs. That's there. Tested the rectifier. That's good. Went through and kind of double checked the caps. They're all really pretty decent. So now it comes down to complicated. Now it has to come down to the logic. Why is the pulse width modulation chip, which is a new chip, I put a new chip in just to make sure that wasn't it, you know, just because I wanted to fix it really. But it wasn't, it didn't help. Actually I replaced all the chips, as I said earlier. Earlier when I started this project, I drew up this schematic. I've got a blow-up version at toddfun.com on a previous posting on this project, which you can download and zoom in on if you feel like helping. And what I'm going to do now is I'm going to basically start looking at the data sheets for those ICs, look at what they actually should be getting to fire, what it's going to take, what voltages they're comparing, and when they're deciding to essentially trigger that pulse width modulation chip. So I'm going to have to go through that in detail to make sure everything else seems fine. So it's probably another weekend, maybe a few more tries, see if I continue with this video format. I'm not so sure anyone likes the video format over the written format. I'm just sort of trying like essentially a video blogging concept where you just have to watch hopefully a short edited video of the things I'm testing and why, to help you out in case you have to troubleshoot such a power supply. But don't troubleshoot power supplies unless you really know what you're doing, because you're dealing with 120 volts and you will hurt yourself if you do not know what you're doing. So this isn't for the novice, but if you ever get there and you want to try it, here's a little information on how to do it. So, perplexing. One of the hardest concepts of power supplies is knowing how those control circuits work sometimes, and we have to figure it out. So, later.